using these Galuzak's law and Avogadro's law to analyze the gas mixtures and to analyze the determination, analyze the organic compounds to find their molecular weights, molecular formulae, and even to extend, we can extend that to find the composition of the mixtures of organic compounds. Let us do a few examples. How can we find the composition of the mixtures? Suppose I want to find the mixtures composition which contains methane and ethane, two different compounds. So by observing the same changes in volumes of the gas mixtures using the ideometer, we can even use that observations to find the composition of this mixture. Say I started a mixture with 10 cc of mixture. So I want to find in this 10 cc mixture how much is methane gas and how much is ethane gas. Even for such determinations also we can use this gas analysis. Say in one analytical work, when this mixture is burnt in oxygen, we find carbon dioxide and water. Suppose the measurements are made under such conditions where water is in liquid state. Say at room temperature, I found when 10 cc of this mixture is burnt completely in oxygen and found the volume of the mixture after the reaction, I found a drastic change in the volume of the mixture. By observing the change in volume of the mixture, how can we find the individual volumes? This is our work. Say in this work I found that after reaction is completed, reaction of combustion completed, volume of the mixture is 22 cc less than initial mixture. I did not know how much oxygen I took here, but no matter. I took 10 cc of this gas mixture containing methane and ethane and I burnt it in excess of oxygen. I might have taken 100 cc, 1000 cc, whatever it is. Surely that should be sufficient and more, but not less. So when this 10 cc mixture is burnt in excess amount of oxygen, I notice at the end of the reaction, the mixture's volume is less by 22 cc than initial mixture. Say initially 100 cc of oxygen, if I use, it becomes 110 cc whole mixture's volume, but after that it is less than that, means around 88 cc only, or whatever it is. The total difference in volume I found 22 cc when I burnt with 10 cc of mixture and excess of oxygen. And from this observation one can tell how much is methane here and how much is ethane. Because it is said the reaction is carried out at room temperature. It's not that it must be carried out at room temperature, but observations made at room temperature. You notice this. Say initially 10 cc mixture I found at room temperature. I took certain amount of oxygen at room temperature. The mixture is taken and measured some volume at room temperature. After reaction is completed at whatever temperature, again when you want to make measurements, you must see that we brought back to this same room temperature. So at that room temperature when I found again the mixture's volume, I find it 22 cc less. This is the meaning of a fall in volume of 22 cc. A reaction completed, the volume is 22 cc less than the initial volume is observation. Now what we do, because the gases are known here, water present, just we want to find the composition. It is methane when burned, it is ethane and burned. Let us write two equations because they are two independent substances, they are getting burnt individually. Gives carbon dioxide, and this gives water, and when you balance the equation, obviously 2O2, here 2H2O, and this is 3.5 O2, and this is 2CO2 and giving 3H2O. But here these we believe in liquid state because set at room temperature measurements made. When every measurement taken at room temperature, whichever is in gaseous state at room temperature only are concerned, because here water and water found in liquid state at room temperature, our problem is only up to this. Remember, in gas analysis, every measurement concerned to gases only to be taken under those conditions where the work is being done. So according to these equations, I don't know how much is methane present, how much is ethane present. Let us say X and Y, Cc of methane and ethane. X Cc methane present, Y Cc ethane present. Total, okay, we know X plus Y given already, that 10 Cc mixture. Now after the reaction, we found a difference in volume. That we express in terms of X and Y again and get the answer like this. Suppose when XCC here is methane reacting, it is combining or reacting with the 2XCC of oxygen and producing XCC of carbon dioxide, and say nothing water. Why not? Water here taken into account because not in gaseous state. So our work is only up to this. Therefore, when you ignore this water's volume which is not in gaseous state, it becomes X combining with the 2X producing X. Similarly, Y combining with 3.5 Y and giving 2Y carbon dioxide. That means in the reaction before the start, the volume was X plus 2X, Y plus 3.5 Y or 7 by 2 Y. And after the reaction, the volume is X plus 2Y. And this difference only he noticed as 22 cc. So the reaction mixture volume before and after, when found a fall of 22 cc. And already we know X plus Y, the total volume given in the beginning, that mixture taken 10 cc. So by solving these two, we can find what is X and what is Y. Like that, individual volumes can be found. And here if you observe in this problem, only one result, one experimental result given. What is that? Before the reaction, after the reaction, the change in volume 22 cc, fall in volume decreased, or the final volume 22 cc less than in the initial volume. So that was sufficient, because here total volume known, individual composition wanted. And the same question the other way also we can get, where individual volume also not given. Then one more observation we need. So we find some further extension needed for the work, and we find another result from same gas analysis and work. Recollect, in the last class we discussed, there are three observations main. One, before and after the change in volume, which is corresponding to change in moles of gaseous substances only. And other is any other individual volumes information, like how much carbon dioxide formed, how much water vapor formed. This we can find by using certain selective absorbents. When selective absorbents are used, like carbon dioxide is to be absorbed by potassium hydroxide, and water vapor by some substance, concentrated sulfuric acid, etc. So by using selective absorbents also it is done. And in this process, sometimes information can be available about the reacted oxygen. So out of these, reacted oxygen volume how much volume change taken place in the reaction, these only again even to analyze the mixer's composition. So we will do another example for a same mixer but without giving the initial volume. So we need some more information. Say, in this problem I am giving a mixture again of methane and ethane gases, and this time I did not tell how much total volume of the mixture also of some composition or some mixture. We don't know exact mixture also. And when I take such a mixture and I want to find individual composition, because the initial volume also is not measured, we can now do it by finding another observation. Volume reactions is same only, but suppose the information given in this way, when methane and ethane gas mixture is burnt in oxygen, after reaction, volume of whole mixture, after the reaction, the whole mixer's volume, say, is, see, this time I am finding more, say 4 cc more than initial volume. This time initial volume is less, final volume is more. Initial volume is less and final volume is more by 4 cc. And the other observation I found here, after passing through KOH, volume again fell. This time he noticed that volume fell by how much? 18 cc, let us say 18 cc. So here notice two observations, two works done. First, before the reaction, after the reaction, change in volume. And after passing through KOH, the volume further decreased by 18 cc. What he is saying is, we this time took the mixture of methane and ethane, burnt in excess of oxygen, and found at the end reaction mixer's volume is more by 4 cc. Next, then that reaction mixer, the products formed, passed through potassium hydroxide